Our focus in this video is on the chain rule and implicit differentiation, both concepts covered in single variable calculus that we now look to extend to functions of multiple variables. Starting with the chain rule, recall that the chain rule states the derivative with respect to x of the composition f of g of x is equal to f prime of g of x times g prime of x. So derivative of the outer function, inner function stays the same, times the derivative of the inner function. Now this works really nice for a function of one variable, but will be a little bit challenging to extend to multivariate functions. So in order to do that, let's define this chain rule in a different way. So same chain rule, we're just expressing it a little bit differently. So let's assume that y equals f of x and x equals g of t. So essentially, if we diagram this out, we have y, which is a function of x, and x is a function of t. Now, not completely necessary for this example, but this little diagram is going to set the stage for what we do in the coming slides. So if we want to express the derivative of y with respect to t, we can first differentiate y with respect to x, and then we're going to differentiate x with respect to t. So we're differentiating the outer function, and then we're differentiating the inner function. Still the chain rule, okay, just expressed a little bit differently, different notation. And this diagram helps us to understand what function is defined in terms of what variables, and then are those variables functions of other variables, which in this case, y is a function of x, x is a function of t. Right? So we've kind of linked together those variables. And just for emphasis here, so going down this, right, that was dy dx, and then going from x to t, differentiate dx dt. Okay, so this expression of the chain rule is the one that we're going to look to extend to functions of multiple variables. So let's take a step in that direction. Suppose that z equals f of x y is a differentiable function in terms of x and y, where x is equal to g of t and y is equal to h of t, and they're both differentiable functions in terms of t. All right, so essentially, just to set the stage a little bit here, we have a function of two variables, and those two variables are functions of another variable. So if we set up a diagram, so we have z up at the top, right? Z is our function in terms of x and y. So we branch out, z is defined in terms of x and y, and then x and y is defined in terms of t. And you can go to a single t here, right? The way you set up your tree diagram, which is what this is referred to, doesn't really matter as long as it makes sense for you. The nice part about a tree diagram, and why we often will use this tool to help us with the chain rule of multivariate functions, is anytime we have multiple branches going down, that means we are taking partial derivatives. So to go down these first two branches, we would take the partial of z with respect to x, or the partial of z with respect to y. And then going down those next two branches, because x is only a function of t, of one variable, y is a function of only t, one variable, we have our single variable derivatives, dx dt, and dy dt. So notation is going to be a key factor in this video and with this concept. We have partial derivatives and single variable derivatives, and it's important that we make the distinction between each. So then dz dt, we have to work our way down each branch that ends in terms of t. So the first part of this derivative is going to be partial of z with respect to x times dx dt, and then starting back up at the top and going down the second branch, partial of z with respect to y, dy dt. So this is our first introduction to the chain rule applied to a function of multiple variables. Z is a function of x and y are both functions of t. So now let's apply this to a problem. So if we let the function f of xy be equal to x squared y cubed, where x equals cosine of 2t and y equals 3e to the t, find df dt. So we already have our tree diagram up here, which is helpful, so we don't have to recreate it for this example. So df dt is going to be equal to, so f in terms of, in place of z, right? Those are interchangeable here. So instead of partial of z with respect to x, we're taking the partial of f with respect to x. So that's going to be 2x y to the third. And then times the derivative of x with respect to t. So that's going to be negative 2 sine of 2t. And then plus derivative of the function with respect to y now. So that's 3x squared y squared. And then we're differentiating y with respect to t. So that's 3e to the t. So there is our function for df dt. If we want it in terms of only t, we would take our x and our y, and we can, so our x and our y, and we can plug in for each x and y in this derivative, right? So that is definitely a possibility. Now, some of you might have picked up on the fact that this wasn't completely necessary in this example, right? And this whole page here. And that's because technically, right, so we could say, we can make a note to ourselves, okay, same as differentiating f of cosine of 2t 3e to the t, right? So we could have substituted x and y in terms of t first and then done a single variable derivative, the normal chain rule in terms of t. The reason we build from this perspective as opposed to substituting in is very shortly x and y are going to be defined in terms of multiple variables, right? So we're going to have more layers to the problem. So taking this approach is going to keep us way more organized. But for this example, we could have plugged in terms of t to begin with and then differentiate, okay, just so we are clear. And it should match the answer we get if we replace all those x's and y's with cos 2t and 3e to the t respectively. Okay, so before we build into those higher level examples, let's stop and do a related rate. I know this is everyone's favorite topic from single variable calculus, so figured it was good to revisit. So the radius of a right circular cylinder is increasing at a rate of 3 inches per minute, while the height is decreasing at a rate of 2 inches per minute. What is the rate of change of the volume of the cylinder when the radius is 4 inches and the height is 6 inches? Okay, so volume of a cylinder, we need an equation to define our related rate. So that's pi r squared h. And then extracting the information here, so the radius, so dr dt, is increasing at a rate of 3 inches per minute. So 3 inches per minute. We won't worry about units right now. And then the height is decreasing, so dh dt decreasing, so that's negative 2. The radius at the moment in time we're pausing at is 4, and the height is 6. So when you tackle this as a single variable problem, you needed to establish some relationship between the radius and the height of the cylinder so that the volume function was in terms of only one variable. But now with this new chain rule that we just defined, we can actually do the problem quite easily the way that it is given right now. So let's make a tree diagram just to really go through this process. So volume is a function of the radius and the height, and we're treating radius and height. And actually, let me just show you another way we can do this one. Okay, radius and height are both a function of t. So anytime multiple branches are coming off, that's partial derivatives. Okay, so we'd have partial of v with respect to r, partial of v with respect to h to go down those first two branches. And then going from r to t or h to t, there's only one branch, so that's a single variable derivative. So dr dt or dh dt. Okay, so we can differentiate or express dv dt. I'll go red, so dv, I want a different color. Okay, so dv dt equals partial of v with respect to r, and then dr dt, plus the partial of v with respect to h, dh dt. So now we just have to find these derivatives, plug in all the information that we know, and solve our related rate. So partial with respect to r is going to be 2 pi rh. dr dt I'll just leave. We have a value for it, but we haven't substituted our values in yet. Partial of v with respect to h, pi r squared, and then dh dt we have a value for. So now we can plug all our values in, right? So dv dt equals, so dv dt equals, so substituting in, so we have 2 pi times 4 times 6, dr dt was 3, plus pi times 4 squared, and then dh dt was negative 2. So dv dt equals, we have 24, 48 times 3, 120, 24, so 144 pi minus 32 pi. So that's going to be 112 pi. And here, if we put minutes in, right, that would be inches cubed per minute. So the volume of the cylinder with respect to time at this moment in time is changing at a rate of 112 pi inches cubed per minute. So this is how a related rate can be tackled with this new style of chain rule. Now let's extend it a little bit further. So now suppose that z is a function of two variables, x and y, where x is now a function of s and t, and y is a function of s and t, and they're both differentiable. So if we start our tree diagram, so we have z up at the top, z branches out, it's defined in terms of x and y, and then x branches out in terms of s and t, as does y. So now at each level, we're using partial derivatives each time. So partial of z with respect to x, partial of x with respect to s, partial of x with respect to t, partial of z with respect to y, partial of y with respect to s, partial of y with respect to t. A little bit cramped in there, okay, but hopefully you can make sense of all of those partials. So if we're taking the partial of z with respect to s, we have to go down the branches so that we end at s each time. So with respect to s, we'd go first differentiate z with respect to x, and then x with respect to s. And then go down the other branch with respect to y, and then with respect to s. Right? So everything in yellow is going to get us to the partial of z with respect to s. So partial of z with respect to x, and then partial of x with respect to s, plus partial of z with respect to y, partial of y with respect to s. And then I'll grab a new highlighter, let's say green. Okay, so then we would go down with respect to x, down with respect to t, down with respect to y, down with respect to t again. And I chose the skinnier highlighter just so that we could see it a little bit better. I'm not sure that worked as well as I thought it would, but we have partial of z with respect to x, partial of x with respect to t, plus partial of z with respect to y, partial of y with respect to t. Okay, so now we have two partial derivatives with respect to s or with respect to t. And again, just like earlier, we could plug in x and y in terms of s and t into the function, get a function with s and t, and then differentiate. But this manner of organizing just makes life a lot easier. Okay, so now let's run through our example here. So function is equal to the natural log of x minus y. x equals s squared plus t squared, y equals st. All right, so we already have our expressions for partial of z with respect to s and with respect to t right above us. Okay, so we'll just use those. So we're going to first differentiate the function. So really this is z, just to make sure, right? This is z. So that our notation matches, right? Or I could have written this as partial of f with respect to s. Didn't really pay attention there. Okay, so with respect to x, we have 1 over x minus y times the derivative of the inside with respect to x, which is 1. And then we differentiate x with respect to s, so 2s. And then plus, now we're differentiating with respect to y. So 1 over x minus y times the derivative with respect to y is negative 1, so I'll negate the numerator. And then differentiating y with respect to s, you get t. And then if we run through that again, but now with respect to t, so still 1 over x minus y, which is nice. We've already done that derivative. And now differentiating x with respect to t now, we get 2t. Still negative 1 over x minus y there. And differentiating y with respect to t now, we get s. And again, we want these functions in terms of s and t. Then plug x and y in. We would accomplish that quite easily. Now here, right, we really start to see where plugging s squared plus t squared and st for y in as a first step and then trying to differentiate could be quite complex. There'd be a lot of moving parts. Whereas expanding them out, treating them as separate functions, and applying this chain rule keeps everything nice and organized. And we can extend this, okay, for as many variables in the original function, for as many variables in our x, our y, our z. Really, it just comes down to creating an organized tree diagram and making sense of whether we're taking partial derivatives or single variable derivatives. So here, function now is in terms of 3 variables, x, y, and z. X is st squared minus t, y equals e to the st, and z equals s plus 3t. So we have our function, 3 branches coming off now, x, y, and z. And from each of these 2 branches, x is in terms of s and t, y is in terms of s and t, z is in terms of s and t. So that tells me we're taking a partial derivative every time we're going down a branch. So partial of f with respect to s, so that's going to be partial of the function with respect to x, and then partial of x with respect to s, plus partial of the function with respect to y, partial of y with respect to s, partial of the function with respect to z, partial of z with respect to s, right? Continuing that chain rule down each branch. So now we have to differentiate. So partial of the function with respect to x is going to give us yz cosine of xz. And then partial of x with respect to s is t squared. And then partial of the function with respect to y is just sine of xz. And partial of y with respect to s is t e to the st. And then plus partial of the function with respect to z is xy cosine of xz. And then partial of z with respect to s is 1. Now here they did give us values. So they told us that s equals 0 and t equals 1. So easy enough to substitute in for s and t, but what do we do about the x's, the y's, and the z's? Well, if we remember, x, y, and z are all functions of s and t, so we can plug in. So x would be 0 minus 1, so x is negative 1. Y would be e to the 0, which is 1. And z over here would be 0 plus 3, which is 3. So just being given s and t is enough to find your x, your y, and your z. And now we can substitute all of those values in. So the partial of the function with respect to s. So y is 1, z is 3, so we get 3 cosine of xz, so negative 3, times t squared, which is 1, and then plus sine of negative 3, and then e to the 0 is 1 times 1 is 1, and then plus xy, which is negative 1, cosine of negative 3 times 1. So we get partial of f with respect to s is 2 cosine of negative 3 plus sine of negative 3. Now, just for a little extension piece here, as a reminder that cosine is an even function and sine is an odd function, if we wanted to express these where the inner part is not negative 3, an equivalent answer would be 2 cosine of 3 minus sine of 3, right? Because sine is odd and cosine is even. Just an important piece to talk about since it is easy enough to extend here. And honestly, it's easier when we get an answer like cosine of 3 and sine 3 because most students aren't going to get stuck with a trig value that they know they should know but forgot in the moment. We just leave it as 2 cosine 3 minus sine 3, and that would be our final answer. Okay, so now that we've established the chain rule, we can extend the chain rule to implicit differentiation. So recall that implicit differentiation can be used to find dy dx. You did that a bunch in single variable calculus. And you did it when you had an implicitly defined curve. Now, the multivariable chain rule is going to give us a simpler method to find dy dx. And it's so much easier that the answer is just going to kind of fall right out as opposed to the amount of work you had last year when you did implicit differentiation problems. And you had to isolate dy dx and solve and move terms around. It's going to become way easier. So the key for making this work is we're going to suppose that an implicit curve can be defined as a level curve of a function of two variables in the form f of xy equals 0. It doesn't have to be 0, it really could be any constant, but typically we try to make it 0 just for consistency, where y is a differentiable function in terms of x. So this little key here is hard for students to wrap their head around, but if you think about a set of level curves, we graphed in the xy plane a bunch of different curves. Right? Maybe 10, maybe 20. There are an infinite number of them, but we only graphed a selection of them. So what we're doing is we're saying one of those level curves is the same as the implicit curve that we're actually trying to differentiate. So because they're the same, we're basically going to change it out. Instead of dealing with the implicitly defined curve, we're actually going to take the function whose level curve is the same. And because we're replacing it with a function, now partial derivatives and operations with functions work better. Okay, so we're starting with the function equaling to 0. Now, if we want to make a tree diagram for this situation, we have capital F is our function in terms of x and y. Now, y is a differentiable function in terms of x, so y is in terms of x, and if we just want to make this complete, x is also in terms of x. That would be our tree diagram. So if we differentiate both sides, with the tree diagram for the left side, we'd have the partial of the function with respect to x, and then dx plus the partial of the function with respect to y, dy dx. And then on the right side, the derivative of a constant is 0. Okay, so by using a level curve set equal to a constant, we can differentiate both sides. Derivative of a constant is 0. And then the left side, we expand that derivative with this chain rule that we've been talking about in this video. There's the dy dx that we're looking for. Dx, this is just going to be 1. So we can very easily solve for dy dx. And that's going to be negation of the partial with respect to x over the partial of the function with respect to y. If you like subscript notation better, it's the negation of partial with respect to x over partial with respect to y. This is going to be much easier for us to compute as long as we remember this. So let's apply it. So find dy dx for x times tangent of y equals 3 plus x squared y squared. So this is an example that you could have been given in single variable calculus. Now we're going to handle it with partial derivatives. So first thing is create the function whose level curve will be, one level curve will be the same as this curve. So let's set it equal to 0. So x tangent of y minus x squared y squared minus 3. So then dy dx equals the negation of the partial of this function with respect to x. So that's going to be tangent y minus 2xy squared over the partial with respect to y, which is x secant squared y minus 2x squared y. Don't forget about that negative right there. That is dy dx. There's implicit differentiation, but using partial derivatives. Again, just for emphasis, right, we're assuming equals 0 is the level curve. That's the same as this implicitly defined curve. So can this be extended to implicit surfaces, right? If it works for implicit curves, can it be extended? And the answer is yes. So suppose an implicit surface can be defined as a level surface of a function of three variables in the form f of x, y, z equals 0, where z is differentiable in terms of x and y. Okay, so essentially now imagine a surface where we can't solve for z to do our partial derivatives, but we still want to find the partial with respect to x and the partial with respect to y. How are we going to do that? Okay, so tree diagram, we have a function. Now we have x, y, and z. So x is only a function of x, y is only a function of y, but z is a differentiable function in terms of x and y. So we start the same way, f of x, y, z equaling to 0 is the level curve that we're changing out. So then differentiating the left side, we have partial of the function with respect to x, and then dx, not a partial there. And then partial of f with respect to y, dy, dy. Actually, not dy, dy. That would have been a mistake. Y is not a function in terms of x. So if we tried to take the partial with respect to x, we would get nothing. And then partial of f with respect to z, and then partial of z with respect to x equals 0. Okay, this is what we're looking for. As I mentioned earlier, this is 0. Y is not a function of x, so its derivative would be 0. And then derivative of x with respect to x is 1. If you wrote this as partial derivatives, that would be fine too. It's still going to be 1. So that middle term goes away. We can solve for the partial of z with respect to x. That's going to be the negation of the partial of f with respect to x over the partial of f with respect to z. Subscript notation, a little bit cleaner. So partial of the function with respect to x over partial with respect to z. And then similarly, partial of z with respect to y is the negation of the partial of f with respect to y over partial of f with respect to z, or the negation of partial with respect to y over partial with respect to z. So as long as we could take some partial derivatives, we're going to get our answer. So our last example in this video, find partial of z with respect to x, partial of z with respect to y for this implicitly defined surface. So we need to set it as a level surface. So we're going to define a function of three variables equal to 2xyz minus x squared minus y squared plus z squared. And again, we're assuming that's equal to 0. That's the level surface that we're working with. So the partial of z with respect to x is the negation of the partial with respect to x. So 2yz minus 2x over partial with respect to z, which is 2xy plus 2z. And then the partial of z with respect to y, negation, partial with respect to y, so 2xz minus 2y, over the partial with respect to z, 2xy plus 2z. And it's that easy, right? Once we establish this function, the implicit derivatives just kind of fall right out with our partial differentiation. So, a lot of notation, two concepts that we were familiar with, chain rule and implicit differentiation, and we looked at how we extended them. Notation, tree diagram, okay, and for the implicit differentiation, basically these memorized formulas that are going to help us out. Hey, go through them, make sure we get comfortable with them, and we'll practice so that happens naturally.